perfect. Do you want me to start? Okay, perfect. Awesome. And then, okay. Cool, okay. Cool. So this is an AI talk a bit more than it is a security talk. How do I have both this up and the other up at the same time?
That is like, it's not possible.
It's not possible?
Yeah, so you can keep it here.
Okay.
See,
Okay,
you
perfect.
can expand it.
Okay, awesome. Sorry for the technical difficulties, but this is a AI talk a bit more than it is a security talk. As engineers, we should really be applying the best tools to the problems, and so that really means taking AI and applying it to solve security problems. I promise this is not an AI hype talk. It's a buzzword that's really everywhere these days, but it is a really good tool for the right problems. And as security folks, we can be naturally skeptics, but we also need to embrace every tool that we have at our disposal, especially when this is the direction that's coming down from leadership. So I wanted to start by polling the room. Who here is using AI in some form at work today? Awesome. Who's using it to write code? Most of you, great. And who is using it to perform code reviews or security reviews? Fewer, but still a good percentage. So it's easier than ever to build software, and vibe coding is pretty magical, but it also gives tools to a lot of people that are not prepared. And unfortunately, here's the same person 2 days later, API usage maxed out, subscriptions bypassed, databases hacked. I'm not trying to attack this particular guy. It's awesome and incredible that software is more accessible now than ever, but it's pretty clear that with more software producers, we're also going to see much more security vulnerabilities. I think it's kind of a Jevons paradox in action. For those who don't know, the Jevons paradox is the idea that more supply paradoxically leads to more demand. So more AI code leads to more AI code, which leads to more need to secure AI code. That's where all of us come in. The need for security is only going to increase, and the need for security experts to actually focus on the most critical areas is only going to increase further still. So when we talk about, why use LLMs to solve problems like AppSec, when applying to AI to any problem, we should think about, is this an appropriate application, or are we just really excited to use a new hammer? Security tasks have a lot of characteristics that align really well with what AI is great at. Requires understanding of diverse context types like code bases, documents, images, rich content from potentially many different sources. The squishiness of LLM inputs also makes them pretty good at comparing across initial design time decisions with final implementation decisions. It requires taking context and transforming that into a normalized output, so you can actually have threat findings in a threat database, put it into your vulnerability management system, and actually see end-to-end what the development looks like. And it's just a computer. So LLMs are very good at consistent, well-defined workflows and frameworks like Stride. They can handle scale and repetition. They don't get tired. They don't get hungry. They don't ask you for a raise. They have infinite patience at developers that aren't doing the right things. So generally, AI is great for AppSec problems. When you should not use AI is when there's unclear goals and outcomes. If you don't know what done looks like, you can't tell a model, this is what done looks like. So humans need to define a process before you can automate it. If there's trade-offs with no clear right answer, when there's a major business decision or business judgment that's needed, you should not be using AI for that. Humans are the right people to make those decisions. And if you don't have any tolerance for probabilistic outcomes, if it needs to be 100% right all of the time and not 99.5%, you should be doing this using deterministic things like code. That is why we all still have engineering components to our systems, and it's not entirely AI. So today we're talking about applying AI to threat modeling specifically. So I grabbed a specific architecture diagram that will threat model, and the same technique can be used for a lot of other security processes, but I thought threat modeling was a really good example to use today. So this is a example service that connects to a bunch of Bluetooth devices. There's an admin portal. There's a kind of server side and a client side. We're going to threat model this. Step 0 is the naive approach, dump it into ChatGPT. And it took a stab at it. We got some high-level information about what the system does, and it even offered to draw me a diagram where it explained where the threat actors were and, visually showing different system components, and that's what it produced. Not great, not a good start. So can't really answer it can great at answering very specific point questions. Using something like ChatGPT is insufficient when you need structure, needs to be systematized, you need methodology, you need to know context about my enterprise environment, my policies. It's more to this than just a simple diagram. So the first big part is building context. That service does not exist in a vacuum, even though it looks like it when you look at an architecture diagram. It's a bunch of white space around the outside, but there's a ton of other context about the enterprise that's missing there. So in order to build context, there's basically kind of a few different components to a traditional concept of retrieval augmented generation. You basically have a concept of a query. What are you trying to retrieve? What is the information that you need? You have a retrieval component that's going to actually retrieve that information or perform a search. A generative component that's taking in that newly searched information and generating new content, and that feeds into the response. Traditional retrieval augmented generation uses a vector store for the retrieval component and chunks the source material. Basic RAG has a time and a place, but there are a lot of limitations. First, the results are entirely dependent on how you chunk it. So you are relying on an embeddings model to determine kind of what those chunks and pieces that are broken down and put into your vector store are and look like. And when you perform a search over these vector stores, you get a set of results that are a bunch of similar things. So similar to looking at a Google search results page, it tells you snippets of contained text that might be similar to what you're looking for, but it's a bunch of sentences that may or may not be actually what you're looking for. Secondly, if you're using a generic embedding model and you're doing something very specific and specialized, like security, all of those embeddings might map very, very close together in the vector space, and so your results might not actually be as relevant as you want them to be. Finally, you actually need to know what you're searching for in order to do this pre-processing and put it into a vector knowledge base. And so you have to have this concept of pre-processing and be like, what do I actually want to search to use this type of basic RAG? So industry as a whole has moved over to more tool use and function calling. Everyone has different definitions of what an agent is, but at the most basic level, it's something that can programmatically perform an actions based on an LM decision. So at a high level, using tool use allows you to use APIs to programmatically search internal systems, the web, call other agents, etc. And it's really RAG 2.0 because you get a lot more context that are not just results from an embeddings model, but are results from different underlying systems. So when we use something like tool use to actually analyze our threat model, we get context like this. So we have that initial architecture diagram that was created. We've also pulled in related tickets from the dev team of different things that they're implementing from Jira. We have context about the organization, who this person is that's submitting this diagram, where do they sit in the broader context of our org, all of our company's internal policies and procedures, and maybe the requirements that are specific to this type of device that's being launched in the EU and therefore needs to be compliant to the Radio Equipment Directive, for example. So once we have something like this, you're able to create a threat model that is much more rich in context. You have contextual diagrams, you're able to break out information via data flows, you're rating threats severities based on your own internal organization policies and risk rating methodologies, documenting what mitigations are present. So great next step. But now what? Cool, we have a threat model, but what's the point of a threat model? It's to find unmitigated issues and tell developers that they should mitigate it. And ideally, give them very clear and pointed suggestions to actually implement it. So you want to take all this information out of this document and put it somewhere, probably into, open findings in Jira or a threat DB. So the next step is actually creating functional structured output and doing this in a production environment. So the requirements for prod are not the same as the requirements for a proof of concept. It doesn't just work. Like, no matter how good the models get, you always need an engineered system because security has very high correctness requirements. If you run ChatGPT 100 times and ask it to output JSON, it might fail 5 times. So you're suddenly not actually opening those findings or tickets because you're just getting these not properly structured errors or other issues, which is why you need to build this engineered system around your AI to actually get the end results that you're looking for. And just to kind of illustrate the point, when we think about it, like if every API call you made failed only 5% of the time, that would be a disaster from an availability perspective. But yet somehow we seem to accept every LLM call failing 5% of the time. And we're security people. Like, our AI apps need to have multiple nines of reliability, accuracy, and consistency. The concepts are just a start. If our security systems fail 5% of the time, like, we're screwed. So when you're thinking about building AI systems in production, you have to think about all of your production requirements and not just have a nice shiny POC that you can demo on ChatGPT, but actually figure out, does this work repeatably and consistently? And that requires a lot of complexity. Agents are hard to build. Tons of things go wrong. There's a huge gap between deploying an LLM and automating your workflows. They hallucinate. They can take your instructions too literally. They have poor taste. They have retrograde amnesia. It feels like 50 First Dates. But there's still a ton of benefit to doing it, right? So how do you think about kind of balancing these things? That would be part 2, building reliability. When I think about a reliable AI system, the first thing I think about is preventing hallucinations. There's a bunch of ways to minimize hallucinations today, and we'll go over a bunch of them. So first, chain of thought reasoning, similar to the idea of as being a student, asking someone to show their work on their math test, they're more likely to end at the proper answer by explaining their reasoning. And a lot of the reason for that is generative AI is generating token by token. So as it's explaining its work, it's actually thinking through the problem to arrive at the correct solution. So chain of thought reasoning is super important, not just so you have insight into what your AI system is doing from an observability perspective, but actually helps you get more right answers. The next piece is source citation and prompt engineering. You have to actually engineer your prompting to give the LM permission to say when information is not present and that it doesn't know. Most of the baseline reinforcement learning models that we're using today have been reinforced to be a helpful assistant. And helpful people like to give you answers. But sometimes the answer is that I don't know. And so you actually have to coax and prompt engineer it into saying, things that aren't said that should be said. Things that are said that are incorrect, like all of those pieces, we need to have prompt engineering in order to say, hey, encryption and rest isn't present, it's not specified, that's a gap, and highlighting where things might be missing. The second piece is source citation. Whenever an LLM posits something, you need to have it link directly back to its end source in order to guarantee that that initial information was not hallucinated. And by asking it to cite its sources, similar to a student with an open book test, it is more likely to be right than if you're trying to think about something off the top of your head. The final piece is LM as judge, and I actually have a demo for this, and that was what took a long time to try to set up properly, so hopefully this works. But I'm going to basically show you how we do LM as judge at Clearly, to give you some ideas of how you can use LLMs to actually help make your LLM processes better.